So in class we talked about some nice simple cations, and I said that there were some issues that probably weren't worth spending class time over, but that you did need to see and become familiar with. Okay, so remember, the main goal is that atoms are all unhappy except the noble gases. Metal atoms like to lose electrons to make cations to try to be happier. So when we look at the periodic table, alkali metals in group 1, they just need to lose 1 electron to become like a noble gas. So K plus is the happy form of K. Alkaline earth metals make 2+ cations because they have 2 electrons past the noble gas, so calcium 2+. And of course, as we pointed out, the same way you'd expect the group 3A metals like aluminum to make 3+ cations, Al3+, and then the group 4 ones to make 4+ cations like SN4+. However, there are several little issues with it. First of all, some of those bigger main group metals can make cations that are 2+ smaller than the ones predicted from the periodic table. And then also transition metals. We deliberately didn't discuss those in class because they are somewhat of a pain when it comes to predicting how they're going to get happier. So let's take these in order. First of all, the bigger main group metals, the larger trials, tetrails and pnictogens. So we're going to be looking at this part of the periodic table. So for example, we go ahead and we look indium. Right? Indium is in group 3, so we would expect it to want to make 3+. However, because it's a bigger one, it can also make a 1+ cation. Reasons for that we won't talk about until chapter 8 if you're lucky, but for now just be familiar with it. And the same idea, thallium right underneath it, Tl, can make Tl+ as well as the expected Tl3+. If we move across the periodic table to the tetrails, and we go to carbon, of course, non-metal, silicon metalloid, germanium metalloid. When we get to tin, it can make tin 4+, but it can also make tin 2+. And then right underneath 10 is Pb lead, that can make 2+ as well as 4+. Then in group 5, in the pnictogens, nitrogen, non-metal, phosphorus, non-metal, arsenic and antimony, both metalloids. So the only metal we have to worry about there is bismuth. Bismuth, you would kind of expect it, if you were being strange, to make 5+. It can also make a 3+ cation. Just need to be familiar with these. You've seen them. Don't be freaked out when we redress these later on. As we said earlier, transition metals are a real pain when it comes to predicting the kind of cations that they make, because they make multiple cations. To simplify the discussion, we'll focus in on just 2 parts of the transition metals. The early transition metals, those that are in groups 3b and 7b, so right there. Most of the time in this discussion we're just going to be focusing on the first row as well. So here, scandium, titanium, vanadium, chromium and manganese. Now first of all, these can make the cation that you would expect them to make. So scandium, if you look at its group, it's in group 3. It's 3 electrons away from being a noble gas, and so it will make Sc3+. Go to titanium, it's 4 electrons away, you've got 4 electrons more than a noble gas, so it will make 4+. Vanadium will make 5+. Chromium can make chromium 6+, and manganese can lose effectively 7 electrons to make Mn7+. So no big deal there. You're thinking, okay, what's the deal with these transition metals? Why did I say they're awkward? Well, because they can also make in-between ones. Every single one of these transition metals up here can make a 2+ cation. So titanium 2+, chromium 2+, manganese 2+. Chromium also makes a very, very, very happy 3+ cation. Manganese, and you'll see this in some of the experiments that you do later on, not only does it make manganese 7+ and manganese 2+, but also manganese 4+ and manganese 6+, and so on. Really, all you got to remember about this is just what we've mentioned, a brief idea of this discussion, and then from there that it is complicated. Now let's go to the late transition metals. These are the ones that are in groups 8b to 2b. So if again we look at the top, iron, cobalt, nickel, copper and zinc. We're also going to mention silver there, gold, and touch on mercury, and just so it doesn't feel left out, we'll talk about cadmium as well. First thing to understand is these never ever ever make the expected cation, the one that you might expect them to make based on our previous conversations in this regard. So for example, iron is in group 8b. If you look at the electrons, it has 8 electrons more than the nearest noble gas, but it's not going to make Fe8+. It's just too tough to lose 8 electrons. All of them do make, except for silver and gold, 2+ cations. Iron, cobalt, nickel and gold also make 3+ cations. So therefore iron we will find as either iron 2+ or iron 3+. Cobalt is cobalt 2+ or 3+, etc. Copper here, silver and gold also make 1+ cations. In fact, really the only time you see a silver cation is as Ag+. Copper you can have as 1+ or 2+. Gold you can have as 1+ or 3+, but silver you'll only ever see that as a 1+. Mercury is kind of a funny little one. There is an anion, or cation, excuse me, Hg2 2+, right, in which we can think of each mercury as having a 1+ cation, but because it's a double metallic diatomic cation, we don't really call it a 1+ cation. But as you'll see later on, there are some things that make us think of it as a 1+ cation. And then finally in this part of it, zinc and cadmium only make 2+. Again, we could spend a lot of time talking about more of these, but as long as you're familiar with what we just discussed, that's going to be quite enough for this course. Finally, you might wonder how we name these cations. When we were dealing with the monatomic cations, it was easy. Sodium, Na, makes Na+, so we call that cation the sodium cation. But when we have more than one cation that comes from one atom, how are we going to name it? For example, iron makes Fe2+ and Fe3+, so we can't call them both iron cations. Well, there are actually two naming conventions for this. The older one that will actually have more words with which you're familiar just uses the metal name, or in some cases even the old name for the metal, and then adds on the suffix us, O-U-S, or ic, depending on which of two cations has the lower or the higher charge. Second, newer way that is much more systematic is where you just say what the charge of the cation by using Roman numerals in parentheses. So a few examples of this just to clear up the confusing wording. Iron makes Fe2+, it also makes Fe3+. Because 2+ is the lower charge, we call that ferrous, right? Again, it's not ironous, it's ferrous. That comes from that old name. And then the new name is iron 2, because it's iron 2+. The other one, Fe3+, again, the old name starts with fer, but because this is the higher charge, it's ic rather than us, so ferric is Fe3+, which in the better way of saying it would be iron 3. Some more examples, and I hope you won't get too bored. CO2+ is cobaltus, cobalt 2, CO3+, cobaltic. Again, notice that the us is the lower, the ic is the higher, and that goes to cobalt 3. Couple that you're going to see a lot, cuprous and cupric, copper 1, copper 2. Okay, and then finally, just using another old word and going into those main group ones that we had, Pb2+ is plumbus. Plum is the old lead indication, hence the symbol Pb. Call that lead 2 now, and then the other option for lead is 4+, which would be plumbic or lead 4.